math people. Today we're going to look at a new technique for solving quadratic equations. This technique was created by Potion Low, the IMO coach for the United States of America. For those who don't know, the IMO is the International Mathematic Olympiad, so the Math Olympiad, but the international one, where the top students from all the countries around the world compete. They basically take a 6-question test when they compete, and the test consists of some of the hardest questions you could imagine. So that's the person that created the technique. I'm going to demonstrate the technique. I'm going to show you the type of problems it's good for and the type of problems it's not so good for. For the problems that it is good for, it is a very good technique. So I'll start off by doing an example using the technique, and then I'll explain after I do the example what actually goes behind in doing what we do for the technique. Alright, so here's the example of a quadratic equation. Let's say x squared minus 32x plus 255 equals 0. And we're going to solve for x. So this is a prime example of a type of problem that this method is very good for. Because for other techniques that we're accustomed to, and when I reference other techniques, I'm mainly talking about the quadratic formula or factoring. Of course, there's other methods, completing the square, graphing. You can also use some numerical methods if you want. But when I refer to other methods, I'm mainly talking about the quadratic formula and factoring. If you look at this problem, to factor it will be quite difficult because a lot of people couldn't think of numbers that multiply to give you 255. Or if you could, it may take you a bit of time to think of all the pair of numbers that multiply to give you 255. And if you're doing the quadratic formula, if you're not using a calculator, squaring 32 and multiplying 4 times 255 could become quite cumbersome. This new method is going to allow us to solve the problem with using arithmetic a lot simpler than what was just expressed. So let me go ahead and solve it by the method. I'm just going to use the method, and then I'll explain why I did what I did afterwards. Okay, so to solve this for x, x will be 16 plus or minus the square root of 256 minus 255. So x is 16 plus or minus the square root of 1. So x is 16 plus or minus 1. So x is 17 and 15. So there's the method. I try to be very descriptive when doing this. A lot of the stuff I was just doing the problem by myself. Of course, I know that 256 minus 255 is 1, and I know that the square root of 1 is 1. So really from here I would just did 16 plus 1, 16 minus 1. But I wanted to be very descriptive so you kind of see how the technique works. Now, if you look at the work that was done, I really only introduced 2 numbers to this problem. 16 and 256, and both of those numbers relate to the number 32, the coefficient of x. 16 is half of that number, and 16 squared is 256. So to get these 2 numbers that were introduced to the problem, I took half of the coefficient of x and I squared it. Doing those 2 things may sound familiar to what is done in a process that is called completing the square. If you see the similarities, you're on to something. Also, you may see when we work this out, I had a number plus or minus the square root of something. That may remind you of the quadratic formula. Also, if you recognize that, you're on to something. However, the method is really based on factoring. In fact, it is a method that will allow me to factor any quadratic you give me, regardless if the roots are rational, irrational, or complex. Mainly when we think about problems, quadratic equations, and we talk about a problem cannot be factored, what we really mean is it can't be factored with rational numbers. But problems can be factored with irrational and complex numbers, and this method can show you how. So let me show you why we did what we did, why we used the 16, why we used the 256. So once again, this is a method that's based off factoring. And we're referring to this type of factoring. So the factoring where you say, okay, I have two parentheses, I have an x here and an x here, and I'm looking for, so this is the old way we would do this, I'm looking for two numbers which multiply to give me 255 and add to give me negative 32. So when I look at this, I notice this is negative and this is positive, so I know both numbers are going to be negative. And so let's say I figure what the numbers are. One number is A and one number is B. So my solution then would be A comma B. So there's a sign change from the factor part to the formula. This should be things that you're all familiar with. Now, the interesting thing about this method, so again, when we normally do a problem like this, what we think about is what numbers can multiply to give us 255 first. When we figure out those numbers, we see which of them add to give us negative 32. This method actually looks at the 32 first and then the 255 second. So when doing this method, I'm not looking at the numbers that multiply to give me 255. I'm actually looking at the numbers that add to give me 32 first. And it acknowledges the fact that there's a sign change from factor to solution, so it already changes the sign from the very beginning. So what this method does is it changes the sign of this number and it puts all its concentration on this guy, the coefficient of x. So this is the main point of emphasis. And it uses a particular law about numbers to find the answer. So, and the law is if I take the average of the two numbers. So right now I know I have two numbers, I don't know what they are, but I have two numbers which add to give me 32. I have no idea what those numbers are, but I know they add to give me 32. So there's a property of math where if you have two numbers and you take their average, so if I have two numbers that have a sum of 32, their average would be 16. So I'm going to call the average x bar. So the average is 16. And if you have two numbers and you know their average, if the numbers are different, if you have two numbers of different value and you know the average of the two numbers, the bigger of the two numbers is going to be a certain units more than the average, and the smaller number is going to be the same number of units less than the average. This is a property of numbers. In this video, I'll give you examples to convince you that it's true. In video number two, I'll prove it in a more formal way. But for this video, to save time, I'm just going to present some information that should convince you that the fact is true. So before I go further, let me convince you that what I just mentioned was true. And by what I mentioned, meaning if I find the average of two numbers, the bigger number is a certain number of units more than the average, and the smaller number is those same number of units less than the average. So I just list three pair of numbers. The numbers don't really matter, so let's say 10 and 24, 15 and 29, 11 and 17. So I just have three random pair of numbers. What I'll do is I'll sum them and find their average and then demonstrate to you that each number is equidistant from the average. And I'll refer to the average as x bar. Okay, so for 10 and 24, the sum is 34. So the average is 17. So x bar is 17. And look at it, 10 is 7 less than 17, and 24 is 7 more than 17. The point we've been making. Let's look at the next pair of numbers. So the next pair of numbers are 15 and 29. 15 and 29, the sum is 44, so the average will be 22. So x bar will be 22. Just look at a draw, I had the difference is 7 again. So 15 is 7 less than 22, 29 is 7 more than 22. And my next pair of numbers, for this, what I don't want, I want one pair where the sum is an odd number. So here again, the sum is going to be an even number. I prefer the sum to be an odd number. So let me just turn 17 to 18, just to show you that even if the sum is an odd number, it still holds true what we're saying. So here I have 11 and 18. The sum is 29, so the average is 14.5. So x bar would be 14.5. And again, you can see 11 is 3.5 less than 14.5, and 18 is 3.5 more than 14.5. So I think we have made a convincing argument, haven't proved it, we'll do that in video 2, but I think we have made a convincing argument that if I have a pair of numbers and I find their average, those two numbers will be equal distance from the average if those numbers are different. Of course, if those numbers are equal, each number is going to be equal to the average, obviously. Okay, so that understanding of a pair of numbers and the averages brought about the following. So back to the problem. Okay, so the average is 16. Alright, so I know I have two numbers. And I know the bigger number is going to be a certain number of units more than 16. And the smaller number is going to be those same number of units less than 16. So say I call that distance from the average to each number, say I call it u. So that means the bigger number would be 16 plus u, and the smaller number would be 16 minus u. So these are the two numbers. I don't know what they are still yet because I don't know what u is, but I know that if I multiply those two numbers together, I'm going to get 255. Now, the beauty in the technique is that this will always be a very easy guy to solve. Very easy to solve. Because you have something plus something times something minus something. That's difference of squares, so we should all be familiar with the formula a plus b times a minus b is a squared minus b squared. So therefore 16 plus u times 16 minus u is 16 squared minus u squared. So this will be 16 squared minus u squared, and this guy of course is 255. And I just leave 16 squared as 16 squared just for right now, so just so you can see some things. We all know that 16 squared is 255. So I'll do the algebra to solve for u. So I'm solving for u. I'm moving stuff to different sides. And what I should get is u squared is 16 squared minus 255. Which then means that u is the square root of 16 squared minus 255. And there's no need to put plus or minus for this particular value of u because the value of u is going to be added and subtracted for some number, so to put plus or minus on this will be superfluous. Okay, so that means in this case, again, 16 plus u and 16 minus u is going to represent our answer. So you can say 16 plus or minus u if you like. So our answer is that x would be 16 plus or minus the square root of 16 squared minus 255. And you know how this calculation ends. 16 squared is 256. And 256 minus 255 is 1. And then you got 16 plus 1, which is 17. And 16 minus 1, which is 15. So everything I just showed you is showing you the background, why we do what we do. But in terms of doing a formula, if you look at it, so let me just rewrite the problem, the original problem. All we have to actually do every time in the problem is take half the coefficient of x and change the sign. There he is. Then do plus or minus and then square that guy. There he is. And then put that number there. So we're doing some pretty simple arithmetic because taking half this number is generally going to be something that's very easy to do. And squaring this number is generally going to be something that's very easy to do. And then this subtraction here is generally going to be something that's very easy to do. So this is a very nice method. Let's look at another example. So let's say we have x squared plus 10x plus 15. So this is another example of a problem that this particular method is very good for. And this particular problem, the roots are not even rational. So you'll still see how the method works with all type of problems. Okay, so let's do the process. So x would be -5. So I'm changing the sign and taking half the number, plus or minus the square root of 5 squared minus 15. So x will be -5 plus or minus, that's 25 minus 15, that's 10, minus the square root of 10, done. So we have completed that problem. And you can see here from the answer that this guy had irrational roots. And even though it had irrational roots, the method still works. Again, this is a method that works for rational roots, irrational roots, and even complex roots. Most techniques you have don't work on all three. Some do. Of course, the quadratic formula works on all three. Completing the square works on all three. But things like factoring and the square root property, those don't necessarily work on all three. This method does. Let's look at another example. So this x squared, let's do minus again, minus 34x plus 200, no, equals 0. Alright. So this is going to be a problem that has complex roots, and still the technique works beautifully. Okay, so let's do it. So x would be 17 plus or minus the square root of 17 squared minus 293. So x is 17 plus or minus 17 squared is 289. 289 minus 283 is -4. So plus or minus the square root of -4. So x would be 17 plus or minus 2i. Complex roots, no problem. So again, very good technique. A very good technique to add to your arsenal for solving quadratic equations. So the question is, if you see the first three examples and it works so seamlessly, the question is, when is it probably not a good idea to use this particular technique? So let me show you a problem that I wouldn't advise you using this technique on. So we looked at three problems where the technique worked very well for. So now let's look at some problems where the technique probably wouldn't be the best. Now you might think, okay, we're going to look at some real crazy difficult problems. No, actually it's going to be very simple. So the simplest of problems, this technique is not the best for. Here's an example. So say my quadratic equation is x squared plus 13x plus 40 equals 0. Now, most of us were taught when solving quadratic equations to first see if you can factor. If you can factor, that's the easiest way to solve. That rule still applies. So this guy could be factored quite easily, and that's the best method to use. So obviously one would notice that 8 times 5 is 40 and 8 plus 5 is 13. So therefore one can see you can factor this guy as 8 plus 5, x plus 8 plus x plus 5, rendering your solution as -8 and -5. That still remains the easiest way to solve this type of problem. The technique we introduced can solve it, no doubt. And I mean, it's not going to be a very difficult process of solving it, but it's not going to be as easy as this when you can see you can factor it with rational numbers. That will always be the easiest way to solve a quadratic equation. But let's look at how our formula deals with this type of problem. And just want to say, the type of problem that this new method is probably not best for is a problem where the coefficient of x is odd. because you know we have to take half this number. So when I take half of an odd number, I'm either going to get a fraction or a decimal, depending on how you like to do it. I'll use fractions. I like dealing with fractions, but either a fraction or a decimal. And I mean, if you're good at dealing with fractions and decimals, it's not going to be that much big of a deal. I'm good with dealing with fractions and decimals. It's not going to be that big of a deal for me to do this that way. However, it's still easier to find 8 and 5 and change the sign. But let's look at it nonetheless. Okay, so x would be negative 13 over 2, that's half of that number, plus or minus the square root of 169 over 4, that's 13 over 2 squared, minus 40. So 40, you need a common denominator. 40 is 160 over 4, so you got 169 over 4 minus 160 over 4. That gives you 9 over 4. So x would be negative 13 over 2 plus or minus the square root of 9 over 4. The square root of 9 over 4 is 3 over 2. So x would be negative 13 over 2 plus or minus 3 over 2. And if you do negative 13 plus 3, you'll get negative 10 divided by 2, negative 5. And if you do negative 13 minus 3, you get negative 16 divided by 2, negative 8. So same answer. It wasn't terribly hard to get the answer with this method. But again, the factoring method was easier. So when the coefficient of x is odd, other methods in many cases will be easier to use than this new method. Let's look at another example where this method is probably not the best method to use. So let's say we have 2x squared minus 7x plus 3 equals 0. Now, this problem is not the best method. It's not the best problem for this method for a couple of reasons. One, because there's a number in front of x squared. We still can use the method, but putting the number in front of x squared just adds an additional item. And then second, again, because that coefficient is odd. So let me look at how we would traditionally solve a problem such as this. We would see if we can factor this. This is something that actually can be factored. And we would do 2x, x, we know we got minus, minus. We'll go to something called trial and error. This problem is not too bad because only 2x and x can give you x squared, and only 3 and 1 can give you 3. When these numbers, when your a and your c have more factors, the problem is a little more complicated. And you play this game of trial and error, trying different factors to make it multiply, and give you this guy. There is a way of doing it called the AC method, where you don't really have to go through the trial and error. You do the AC method and apply something called factoring by grouping, which is good for the problems when it can be factored and there's a number in front of x squared. But this one is fairly easy to factor, and I think you would see that I'll put a 3 here and a 1 there. And if I multiplied all that out, I get 2x squared minus 7x plus 3. So that means that the solution then would be 1/2 and positive 3. So if you could see how to factor, factoring is the easiest way. But a lot of times when there's a coefficient in front of x squared, sometimes the factoring is quite difficult for people. This one was an easy example, but you know, it can be a little more complicated. So in a problem where there's a number in front of x squared and you can't see how to factor, perhaps the quadratic formula will be the easiest way of doing that problem. Because in a quadratic formula, I'm not going to be dealing with any fractions. So I'll look at the quadratic formula real quick for this problem, and you should be familiar with the quadratic formula. If you're not, shame on you. So if I'm doing this by the quadratic formula, I'll get that x is 7 plus or minus the square root of 49 minus 4 times 2 times 3 all over 2 times 2. So I'll get that x is 7 plus or minus This is 49 minus 24, that's 25. The square root of 25 is 5. So 7 plus or minus 5 over 4. And when I do 7 plus 5 over 4, that's 12 over 4, that's 3. And when I do 7 minus 5 over 4, that's 2 over 4, that's 1/2. Again, the same answer. Still got it fairly quickly. All these methods, we're going to get the answer in a matter of seconds. But again, if I can see the factor, that will always be the easiest case. And if I'm doing a quadratic formula, you'll notice these were fairly simple calculations to make. But I can do most of these calculations just dealing with integers. And I really don't deal with fractions until the very end. When we do the new method, because this number is odd, it's going to require the application of fractions again, which for some people can cause some issues. Now, here's the deal. So the method we've been using is a method when the coefficient of x squared is 1. So when you encounter a problem where the coefficient of x squared is something other than 1, just divide out that coefficient and make the coefficient of x squared 1. So to do this problem by the new method we've been speaking of, we have to first divide everything by 2. And so we'll get x squared minus 7 over 2x plus 3 over 2. That of course equals 0. Again, now quite honestly, if you were to graph this function and graph this function, they wouldn't be identical. They're not the identical functions, but their x-intercepts would be the same, so their solution is the same. So we're all gained if we solve this guy. The solution will be the same as the solution of this guy. Okay, so let's do the process. So x would be, I'm going to change the sign of this number, take half of it, so that would be 7 over 4. So 7 over 4 plus or minus the square root of 49 over 16 minus 3 over 2. Again, if you're conversant with doing mathematics with fractions, still not that big of a deal. So x would be 7 over 4 plus or minus, let's see, so 3 over 2 needs to have a denominator of 16, multiply top and bottom by 8, that would be 24 over 16. So that would be 49 over 16 minus 24 over 16, which would give us 25 over 16, and the square root of 25 over 16 is 5 over 4. So 7 over 4 plus or minus 5 over 4. And if you notice, pretty similar to what we had inside the radical when we were doing the quadratic formula, quite honestly. And so again, if you look at it, if you do 7 over 4 plus 5 over 4, that's 12 over 4, that's 3. And if you do 7 over 4 minus 5 over 4, that's 2 over 4, or 1/2. So again, not terrible, but probably not the best method to use for this particular problem. So that concludes our new method of solving quadratic formulas for solving quadratic equations. And again, I think what we demonstrated is a method that's very good for problems when there's not a coefficient in front of x squared and the coefficient of x is even. It will solve all of those types of problems quite nicely, irregardless of if the roots are rational, irrational, or complex. When the coefficient of x is odd, and or there's also a coefficient of x squared, that's when the usefulness of this particular technique tends to be wanting. So maybe it's not recommended for those. I hope you enjoyed the new method. It's just a new technique you can add to your arsenal for solving quadratic equations. Until the next time we see you, have a good day.